A wooden schooner called the Island Queen was making a routine voyage. On board were more than 60 people, passengers and crew, going about an ordinary day on an ordinary route they'd traveled countless times before. And then the Island Queen vanished. No distress call, no survivors, no wreckage, nothing. At the time, the most obvious explanation was war. It was 1944. German U-boats prowled the Caribbean. Allied submarines patrolled these waters too. The assumption was that the Island Queen had been torpedoed, caught in the crossfire of a conflict thousands of miles from its origin. But here's the thing about torpedoes. They leave evidence. Debris, oil slicks, bodies, something. The Island Queen left nothing. The boat, the cargo, the 60-plus souls on board, all of it simply disappeared, as if the ocean had opened up and swallowed them whole. For decades, it remained one of Grenada's worst maritime tragedies, an unsolved mystery filed away and mostly forgotten, until scientists started looking at what else was happening in those waters that year. Because in 1943, just 1 year before the Island Queen vanished, something had erupted on the seafloor about 8 kilometers north of Grenada, something that was almost certainly still active, still releasing gas into the water column in August of 1944. And if that's what happened to the Island Queen, it would explain everything. The lack of debris, the lack of bodies, the complete and total disappearance. Because when water stops being water, when it fills with enough gas to change its fundamental properties, ships don't sink the way you'd expect. They drop. Straight down, and everything on board goes with them. To understand how this works, we need to go back to some very basic physics, the kind you probably learned in middle school and then promptly forgot. Archimedes' principle, you've heard of it. An object submerged in fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. In simpler terms, things float when they push aside enough water to counterbalance their own weight. A ship, even a massive steel cargo vessel weighing thousands of tons, floats because of its shape. The hull is hollow. It contains air. When you calculate the average density of the entire ship, including all that air inside, it comes out lighter than the water it's sitting in. That's why ships float. Not because they're light, because they're less dense than the water around them, but here's where it gets dangerous. What happens if the water itself becomes less dense? Imagine you're floating in a swimming pool. Now imagine someone starts pumping air bubbles into the water from below. Millions of tiny bubbles, saturating the water around you. The water is still there. You can see it, feel it, but it's now a mixture, part water, part gas. And that mixture weighs less than pure water, which means your body, which was perfectly buoyant a moment ago, is now denser than the fluid around it. You sink. The same principle applies to ships. If the water beneath a vessel becomes sufficiently aerated, filled with enough gas bubbles to significantly reduce its density, the ship can no longer displace enough weight to stay afloat. It doesn't capsize, it doesn't take on water, it just drops. Sailors have a name for this. They call it white water, because when the ocean fills with gas, it froths, it foams, it turns pale and milky, and if you're unlucky enough to be sailing through it when it happens, you might not have time to understand what's going wrong before your deck is underwater. So where does this gas come from? The ocean floor. Buried beneath the seabed, in sediments hundreds of meters deep, there exist vast deposits of something called methane hydrate. It's essentially frozen natural gas. Methane molecules trapped inside a lattice of ice crystals, kept solid by the immense pressure of the deep ocean. These deposits are everywhere. Continental shelves around the world are laced with them. The Blake Ridge, off the southeastern coast of the United States, contains one of the largest known concentrations. The North Sea between Britain and continental Europe has significant reserves. The Barents Sea in the Arctic is riddled with them. Under normal circumstances, methane hydrates just sit there, inert, harmless. But if something disturbs them, a submarine landslide, a shift in water temperature, a change in pressure, they can destabilize. The ice lattice breaks apart, and the methane, suddenly freed, transforms from solid to gas that rises. In 2016, researchers at the Arctic University of Norway announced the discovery of something alarming on the floor of the Barents Sea, enormous craters, some of them half a mile wide and 150 feet deep. These weren't impact craters. They weren't geological formations shaped over millions of years. They were blowout sites. According to Professor Karen Andreasen and her team at the Center for Arctic Gas Hydrate, Environment, and Climate, these craters were formed by explosive releases of methane gas, eruptions powerful enough to blast holes in the seafloor. The eruptions they documented happened thousands of years ago, during the last deglaciation, but the deposits that created them still exist, and similar deposits exist in oceans around the world. Now, to be clear, there's no verified record of a methane hydrate eruption sinking a ship in modern times. Benjamin Frampus, an earth scientist at Southern Methodist University, has pointed out that large-scale methane releases haven't been observed in recent history. But the possibility is real enough that scientists have studied it, and in at least one location, the threat is taken seriously enough to enforce an exclusion zone. 8 kilometers north of Grenada, beneath roughly 200 meters of Caribbean seawater, there's an underwater volcano called Jenny. It's not a particularly large volcano. Its summit doesn't break the surface. Most people sailing through the Grenadines have no idea it's there. But Jenny is special. It's the only confirmed active submarine volcano in the Eastern Caribbean, and it's one of the most active volcanoes in the entire region, erupting at least 14 times since it was first identified in 1939. The volcano isn't just dangerous because it might erupt. It's dangerous because of what it does constantly, even between eruptions. It releases gas. Submarine volcanoes emit large quantities of gas bubbles into the surrounding water, even during quiet periods. This can lower the density of the seawater above the vent. And according to the University of the West Indies Seismic Research Center, the scientists who monitor Jenny, this is very dangerous to shipping. Their exact words, boats entering a zone of lowered water density will lose buoyancy and may sink. That's not speculation. That's not a theoretical concern. That's a direct warning from the scientists responsible for monitoring the volcano. And it's why Jenny has a permanent exclusion zone. Under normal conditions, all vessels are required to stay at least 1.5 kilometers from the volcano's summit. When seismic activity increases, which happens regularly, that zone expands to 5 kilometers. The alert level is kept at a constant yellow, the second lowest on the scale, because the danger never fully goes away. The shipping route between Grenada and St. Vincent passes close to Jenny. Fishermen work these waters, recreational sailors cruise through, and all of them are warned, stay away from the volcano. Because the Island Queen, the schooner that disappeared without a trace in 1944? According to the UWI Seismic Research Center, that tragedy may have resulted from just this phenomenon. Jenny had erupted the year before. It was highly likely still degassing in 1944. And the complete lack of debris, the total disappearance of everything on board, is exactly what you'd expect if a ship suddenly lost buoyancy and dropped straight to the seafloor. So we have a plausible mechanism. We have at least one location where authorities take the threat seriously enough to enforce an exclusion zone. We have a historical tragedy that might have been caused by this phenomenon. But has anyone actually tested it? In 2003, 2 researchers at Monash University in Australia decided to find out. David May and Joseph Monaghan designed an experiment to determine whether a gas bubble rising from the seafloor could actually sink a ship. Their setup was elegant in its simplicity. They trapped water between 2 vertical glass plates, creating a narrow tank. They placed an acrylic model ship hull on the surface, and then they released gas bubbles from the bottom and filmed what happened. What they found was published in the American Journal of Physics, one of the most respected peer-reviewed journals in the field. The answer to, can a single bubble sink a ship, turned out to be yes, under specific conditions. But the specific conditions matter. A lot. May and Monaghan discovered that a ship's survival depends entirely on its position relative to the rising bubble. If the ship is far from the bubble, safe. The bubble rises, breaks the surface, and the ship is unaffected. If the ship is directly above the bubble, also safe. At the center of the bubble's rise, there's what physicists call a stagnation point. The ship essentially rides the bubble up and settles back down. The danger zone is in between. If a ship is positioned between the bubble's center and its outer edge, it gets carried into the trough created by the rising gas, a depression in the water's surface. The ship tips, water floods in, and it sinks. The researchers were motivated by more than academic curiosity. They'd been studying something called the Witch's Hole, a known methane eruption site in the North Sea between Britain and continental Europe. Sonar surveys of the Witch's Hole had revealed something intriguing, a sunken vessel sitting in the exact center of one particularly large eruption crater. The ship was upright, its nets and deck equipment were intact. It looked like a late 19th or early 20th century vessel. No one has ever identified that ship or determined why it sank, but its final resting position, dead center in a methane blowout site, is consistent with exactly the phenomenon May and Monaghan studied. But hold on. If this phenomenon is real, why aren't ships sinking all the time? Methane seeps exist all over the world's oceans. Underwater volcanic vents release gas constantly. If bubbly water could sink ships, shouldn't we be seeing it happen? There's a counter-argument here, and it's worth taking seriously. In 2010, a physicist named Michael Hushen published a follow-up study in the same journal, the American Journal of Physics. He'd noticed something the Monash researchers hadn't fully accounted for. When bubbles rise through water, they don't just reduce density, they also create currents. The rising bubbles drag water upward with them, generating what's called an upwelling flow. And that upwelling flow can actually push floating objects up, not down. In Hution's experiments, his model ship floated in foam with a density of only 0.75 grams per cubic centimeter, significantly less dense than the ship itself. By the math, the ship should have sunk, but it didn't. The upwelling currents from the rising bubbles kept it afloat. This matches what Mythbusters found when they tested a related myth. In their Bubble Trouble episode, they tried to determine whether a swimmer would sink in aerated water. The answer was no. The bubbles created convection currents that pushed the swimmer up, not down. Helen Chersky, an oceanographer and physicist at University College London, has been even more direct in her skepticism. In an interview with Tech Insider, she pointed out that modern ships are specifically designed to handle disturbances on the surface. Her assessment: the only thing this phenomenon is capable of sinking is a really crappy ship. For a methane bubble to actually capsize a vessel, she explained, the ship would have to be already heavily tilted to one side. Otherwise, the bubbles would just push it around. Annoying maybe, but not catastrophic. And there's one more piece of evidence worth considering. A thesis study from Texas Tech University examined 15 actual offshore oil and gas blowout incidents, situations where massive amounts of gas were released near drilling platforms and vessels. The finding? Density reduction from gas in the water was not the cause of any rig or vessel sinking. Fire caused sinkings, explosions caused sinkings, flooding through open hatches caused sinkings, but the mere presence of gas bubbles in the water? Not once. So, which is it? Can bubbles sink ships, or can't they? The honest answer, as with most things in science, is it depends. The Monash experiments demonstrated that sinking is physically possible. The follow-up studies demonstrated that real-world conditions usually prevent it from happening. The key word there is usually. For a gas bubble to sink a ship, several conditions need to align simultaneously. First, the bubble needs to be big enough. May and Monahan found that the bubble's radius of curvature needs to be comparable to the ship's hull length. A cloud of tiny bubbles won't do it. You need a single massive release of gas. Second, the ship needs to be in exactly the wrong position. Not directly above the bubble, not far away from it, right in that danger zone between the center and the edge where the trough forms. Third, there can't be significant currents or other disturbances that would generate the upwelling effect Hution identified. In a static system, like a calm, confined body of water, the physics works. In the open ocean, with waves and currents and multiple bubble plumes interacting, the situation becomes much more complicated. And fourth, the release needs to be sudden. A slow seep gives the ship time to move, gives the water time to equalize, gives the crew time to realize something is wrong. An explosive blowout, like the ones that created those craters in the Barents Sea, would give no warning at all. All of these conditions coming together at once is rare. Extremely rare. But rare isn't impossible. And in a place like Kikum-Jenny, where the volcano is constantly active, where gas releases happen regularly, where the conditions might align just right on any given day, the authorities have decided the risk is real enough to enforce an exclusion zone. That's not superstition. That's risk management based on physics. There's one more scenario worth considering. It's more speculative than everything we've discussed so far, but it might explain something that's puzzled sailors for centuries. You've probably heard the old warning, if a ship is sinking, swim away from it as fast as you can, otherwise you'll be sucked down with the vessel. The traditional explanation is that the sinking ship creates a vacuum, a void in the water that pulls everything nearby into the depths. But that doesn't quite make physical sense. Water is incompressible. You can't create a vacuum in it. The water rushes in to fill the space left by the sinking hull, sure, but the forces involved shouldn't be strong enough to drag a swimmer down. So what's actually happening? One theory, it's not suction, it's aeration. When a large ship sinks, all the air trapped inside, in compartments, in cabins, in the holds, comes bubbling out. A massive vessel can release an enormous volume of air as it goes down, and all that air has to go somewhere. It goes up, through the water, creating a column of froth directly above the sinking ship. And we've already established what happens when water fills with bubbles. Its density drops. Objects that were buoyant a moment ago suddenly aren't. You don't get sucked down, you fall, through water that has temporarily stopped being able to hold you up. This theory is harder to verify than the seafloor methane hypothesis. No one has conducted controlled experiments on sinking ships with swimmers nearby for obvious ethical reasons, but the physics is consistent, and it would explain why the advice to swim away from a sinking vessel has persisted for so long, not because of suction, because of aeration. If you're treading water directly above a sinking ship and all that air comes rushing up around you, you might find yourself suddenly unable to stay afloat. By the time the bubbles clear and the water returns to normal density, you'd already be deep underwater. So let's bring this back to where we started. The Island Queen, more than 60 people, vanished without a trace in 1944. Did whitewater kill them? Did a release of volcanic gas from Kikum-Jenny turn the ocean beneath their hull into something they couldn't float on? The honest answer is, we don't know. We can't know, not with certainty, not after 80 years with no wreckage and no survivors. But we can say this: the physics is real. Lab experiments have demonstrated that under the right conditions, a gas bubble rising from the seafloor can sink a ship. The threat is taken seriously. Jenny has an enforced exclusion zone specifically because of this danger. The scientists who monitor the volcano explicitly warn that boats entering a zone of lowered water density may sink. The historical pattern fits. The Island Queen disappeared 1 year after Jenny erupted, while the volcano was likely still actively degassing. The complete lack of debris is exactly what you'd expect if the ship dropped straight to the seafloor. And there's at least one other unexplained wreck: the vessel in the Witch's Hole, sitting at the center of a known methane eruption site, as if the ocean simply opened up and swallowed it. But real-world conditions usually prevent this from happening. Currents and waves create upwelling effects that keep ships afloat. Multiple bubble plumes behave differently than single large bubbles. Modern ships are designed to handle surface disturbances. The 15 offshore blowouts that have been studied didn't sink any vessels through density reduction alone. Scientists who've examined the Bermuda Triangle hypothesis have concluded that methane bubbles probably can't account for more than a handful of disappearances, if any. And statistically, there are no more unexplained sinkings in areas with known methane deposits than anywhere else in the ocean. The Bermuda Triangle itself isn't even recognized by the US Navy or the Board on Geographic Names as a distinct region. As the National Oceanic and Atmospheric Administration puts it, the ocean has always been a mysterious place to humans, and when foul weather or poor navigation is involved, it can be a very deadly place. This is true all over the world. Or as one Coast Guard lieutenant more bluntly stated, the combined forces of nature and human fallibility outdo even the most incredulous science fiction. So, is the whitewater phenomenon real? Yes, under specific conditions that rarely occur outside laboratory settings. Can it sink ships? In theory, yes. In practice, almost never. Did it kill the passengers of the Island Queen? Maybe. Possibly. We'll probably never know for sure. But if you're ever sailing near Jenny and the water starts to look pale and frothy, if the ocean begins to foam for no apparent reason, don't wait around to find out. Steer away. Fast. Because the one thing we know for certain is this: the scientists who monitor that volcano, the ones who understand the physics better than anyone, have decided the risk is real enough to enforce a permanent exclusion zone. And they probably know something the rest of us don't.